Back in the Stone Age, before nerds invented iPhones, Windows, or running water, IBM was getting pretty good at forcing fancy rocks to do their bidding. But they had a problem. They desperately needed a portable way to move data around. Hard drives were impractical due to their room-filling nature, seek times a magnetic tape made random access borderline unusable, and they couldn't hire enough boxers to punch cards. They needed something brand new. They needed something revolutionary. Thus, IBM did what IBM does, and sued the IRS for $13 million. Luckily, the legal department is separate from engineering, so the lab boys got cracking, and set all their best minds on producing a small, light, and portable data storage medium. The engineers did not do that.
The IBM Magnetic Disk Pack, an important element in information processing.
They made the Disk Pack, weighing in at 10 pounds and looking like a cake tray. Released a year later, they sold like hotcakes, presumably due to their vast similarities. With that failure out of the way, the legal department finally won their lawsuit, giving IBM enough cash to try again. This time, their only goal was to shrink down the Disk Pack into something at least slightly smaller than a birthday cake. Originally read-only and used for glorified BIOS updates, the humble 8-inch floppy disk rose to power, storing only 80 kilobytes of data, or about this much Daft Punk. Hilariously, the first commercial use of this disk was to hold the microcode for a more traditional platter-based storage add-on for the mainframes that IBM was selling at the time. Luckily, some other nerds nearby took note of the vast possibilities of this new semi-erect format, and one such nerd at Memorex started selling read and write floppy drives, holding 175 kilobytes each, or about enough Daft Punk to get this video taken down. What's that? You've never heard of Memorex? Well, me neither. They went bankrupt. Time continued to pass, and the floppy disks slowly became smaller, higher density, and cheaper, but were still above average at a monster 5.5 inches per side. Luckily, the Japanese caught wind of this and wouldn't let that stand, and Sony perfected the floppy disk down into the previously ubiquitous 3.5-inch floppy that we knew and loved. Then crunched it down another inch to fit into the first still video camera, the Sony Mavica, which is apparently distinct from a digital camera for nerd reasons that you can read about on Wikipedia. Hey guys, my name's DocJade, and welcome to my current magnum opus. Today we'll be beating Factorio on floppy disks. Just a heads up, this video is going to be quite technical, but even if you don't understand everything I'm saying, it should still be entertaining. There's a couple ways I could do this. I could do this the easy way by making a bunch of floppy-sized files and opening them one by one in a virtual machine, but I consider that cheating, since no actual floppy disks ever get used. We'll be using real disks. I could do a giant RAID array, but that has been done before, and I'd need a floppy drive for each disk. Windows does not like having a lot of USB devices plugged into it, so that's off the table. Not to mention that it would cost over $10,000 to buy all the drives I need, but whatever. So I bought one drive, and a backup drive just in case. But obviously, the game isn't going to fit onto a single floppy. The modern double-sided high-density disk only holds about 1.5 MB per disk, or about one photo from my phone. So we'll have to spread out the game across multiple disks. A lot of disks. Over 1,000 of them. Fun fact, they don't make floppy disks anymore. And buying old stock off of Amazon would be way too expensive, but luckily, Tom over at floppydisk.com was able to hook me up with 1,250 disks. Interestingly, just a few days before I went shopping for the disks, AOL announced that they would be discontinuing their dial-up internet service, which they'd been running since 1991. 34 years. Why is this relevant? Well, to advertise this service, AOL used to mail out tons of free trial disks, and apparently they had a lot left over. Guess where they ended up? I now have around 250 years of late 90s AOL free trial, which at 1999 speeds of around 56 kilobits per second is over 55 terabytes. Now with a considerably lighter wallet and boxes full of crap that's older than me, I still have to figure out how to actually put the game on them, but I can only have one disk in the drive at a time. Searching online, I wasn't able to find a file system that both supported splitting files between multiple disks, while also letting you access every file without all the disks connected, because why would anyone want that? So naturally, I wrote my own. To be able to play the game later, we're obviously going to need to put the game onto the floppy disks, since right now they're just full of a bunch of AOL crap, so I'll start doing that in the background. Most of you probably don't know what a file system is, so here's a brief overview that'll annoy experts. We'll talk about how everything works in more depth later. Storing information on computers is a pretty complicated task. Well, not really. Storing data somewhere is easy, but getting it back is the hard part. You can think about all the storage on your computer, such as your hard drive, as a library. You have shelves upon shelves of books that store all of the information you need, but you need a librarian to keep everything organized and help you find what you're looking for. That's what a file system is. Broadly speaking, there's two things in our library. Files, which in our analogy are like books. Everything from the video you're watching right now to that 3 GB picture of your mother I have on my desktop is a file. Files are where we store our data, but that's all they do. They're just a whole heaping spaghetti pile of informazione. So we also have directories, also commonly called folders. Directories are like bookshelves, purely for organizing our files. Do note that you can put bookshelves onto other bookshelves, but just pretend that makes sense. So the file system's job, or the librarian's job, is just to keep everything organized and give us the books we're looking for. Slight problem though, I've never worked in a library, and I've never worked with file systems before, so writing the game to the disks didn't go very well. The early versions of the file system, which the file system is named Fluster, came together pretty quickly, and I was able to get Bad Apple to play off of just a few disks. Yes! Yeah. It works! For 3 seconds. But as every developer knows, it doesn't get bad, it gets worse when you scale up. Due to many oversights and not planning on disks failing, I had to restart writing the game several times while also rewriting core functionality of the file system. But eventually, I did have the entire game on disk. Now I just needed to load it in. Traditionally, if you wanted to play a game that came on multiple floppy disks, you would install the game from the disks by copying all the files over to your main hard drive from the floppy disks, and then running it off of your hard drive. But I just spent all this time putting the game onto the disks. Copying it all back off again to put it into a folder that I just copied it out of would be stupid. So instead, Fluster is a bit special. You can actually play the game, or any game really, it's a fully implemented file system, directly from the disks. Fluster will just prompt you whenever it needs a file from a different disk, so you'll go and grab that disk, swap it in, wait, go grab another disk, swap it in, wait, and so on and so forth for a while until it loads in the file that the game was requesting. For most games, this would be an awful idea, but thankfully Factorio loads in almost the entire game before hitting the title screen. So once you've hit the title screen, almost everything is loaded, except for a few exceptions like, sound. As you might imagine, since we're loading in everything at once, that might take a while. You're absolutely right! Every day, sunrise to sunset, this is all I did. For over a week. If I played all the time-lapse footage I captured at this speed, we'd be here for over 2 hours. So let's move on. Now that the game is finally loaded, I can officially say that to play Factorio on floppy disk, it'll take you 3 months and 2 pounds of hair to get to the title screen. Due to some holes in the file system, such as, file locking, a few things don't work, such as hitting new game. This is a super old screen recording, but you get the point. So I've pre-prepared a save to start with. But now that the game is loaded, we can just play it. Well, like I said, sound isn't loaded yet, so randomly the game will completely lock up until I swap disks around to load a sound, but yeah. But once the sound loads, it looks like Windows does cache it for quite a while, so it's not a super big deal, it's just annoying at first. Originally, I kept every single time the game froze into the video, but it got really boring, so I've edited out all of it. Anyways, as usual, iron, rocks, coal. Fun fact about the map, if I click the Roboport button, the game crashes. I have no idea why that happens, and I was never able to figure out a way to fix it, so we'll just not do that. And that's Steam Power, which I had to swap disks to load the sound for. Copper, electronics, and red science. I usually try to be pretty in-depth with most of my videos gameplay-wise, next up is automation and logistics, but the interesting part of this playthrough is the technical side, not the actual gameplay, so I will skip around a bit more than usual. Speaking of the technical side, I'll be explaining how Fluster works while we play. If you don't understand something, that's fine, I don't understand it either. Wait, why did I even use chapters? There's only 3 of them. Now, let's talk implementation specifics. The extent of my knowledge on file systems before this was mostly that, files live on the disk somewhere and they get pointed to, and that the Nintendo Wii used blocks for some reason. I didn't know what a block was, but I do now. Anyway, I needed to learn a little bit more before jumping in headfirst and writing my own, so I did what every sane person would do, and I just skimmed the Wikipedia page and called it a day. Yeah, I have a really bad habit of not thoroughly researching things before learning how to do them, and this time was no exception. So let's get started. Fluster is written in Rust, which might make some of you mad, and most of you won't care. As for why, well, mostly just because I like Rust, and it usually stops me from shooting myself in the foot. Also, the only other languages I have a lot of experience in are Python and PowerShell, which probably wouldn't have worked very well. Oh, and if you're really smart and you think some of my decisions or implementations that I came up with are a little wonky, they probably are. I'm self-taught. I don't know best practice. Anyway, I started brainstorming the disk format in as much detail as I could, so I could have a good outline of what I wanted to implement and how I wanted to implement it. The first design doc outlined pretty much everything I could think of and ended up being surprisingly close to the final implementation. But some ideas like dense disks were thrown away for the sake of simplicity, so take everything here with a grain of salt. Dude, I made the exact perfect amount of furnaces. This is the first time this has ever happened. Anyways, blocks. Each disk was broken into 512-byte blocks. I didn't want to go with too large of a block size, since any unused space in the blocks would add up quite quickly. This broke every disk into 2,880 512-byte blocks, and each disk got a header block that stored the magic fluster string to mark the disks, and various other information like the number of the disk and the block usage bit plane. Using 2 bytes for the disk number does limit us to at most 6,536 disks, which would hold a theoretical maximum of around 90 gigabytes of storage. But, oh well, I'm not planning on installing COD, so it's fine. Surprisingly, 2,880 is divisible by 8. I don't really like that fact, but it does give us 360, which is how many bytes are reserved for the block usage bit plane.
Mama Lizzie's chili oil.
The block usage bit plane is put into the header to let us keep track on each disk which blocks are located, and this prevents us from needing to keep track of it somewhere else or infer it based on pointers. It just makes things simpler. The header block always lives at block 0 on the disk. We're programmers, we start at 0, but the rest of the disk can be a mix of any of the other block types, which ended up being directory blocks, file extent blocks, INO blocks, and raw data blocks. Regardless of block type, the last 4 bytes of every block are dedicated to a CRC checksum, which is a tad overkill, but it should let us detect disk corruption very accurately. Not that we would be able to recover from it, but it's nice to have. I really like to build things from the bottom up, so with all my plans on the table, I finally read the first bytes off of an actual disk. At this point, I was still running directly on Windows, more on that later, which made reading the disk as simple as reading from the A drive, which always maps to any floppy drive in the system. After confirming that worked correctly, I started putting together a block interface for reading and writing directly to the disk. Eventually, I came up with disk pointers as a way to keep track of what blocks came from where, which made passing around blocks easier since it's always nice to know where they're coming from and where they're going. Disk pointers are just a pair of 16-bit numbers. The first one stores which disk the data is from, and the second stores what block it's from. Using a disk pointer, you can reach out directly to the floppy drive to read a block off of the disk, which returns a raw block. When you read a block, you get 512 bytes and the origin of that block. That's it. That's all a raw block is. But enough abstractions were built on top of this that eventually you could pass around other block types and read the disk using an interface called the floppy drive, but explaining that is out of scope. With a proper block level interface built out, I could finally start reading and writing to the disks in a sensible way, and finally got the fluster text onto a disk for the first time. The fluster text is a magic number that we use to deduce if a disk has already been set up to be used with fluster. If that string isn't there, we assume it's just some random disk and we'll ask if you want to wipe it or something. If you want to read from the floppy disk, you gotta reach out to the floppy drive, which then has to move the little heads inside of the floppy drive into the right spot, wait for the disk to spin around to the part that has the data that you want on it, and hopefully read 512 bytes in a row. But sometimes the whole 512 bytes won't be on the same tracks and then I'll have to move the head again. Yeah, it's really slow. So pretty early on, I set up another layer of abstraction to pretend that a random file on my machine was a floppy disk, which sped up development a lot. With actually touching the disk and moving blocks back and forth out of the way, I started to work on actually pooling multiple disks together. Naming things is hard, so this is called the disk pool. Information about the pool is stored onto disk 0 using its own special header. At one point, I planned on storing a bunch more information about the pool onto the pool disk, like keeping track of where disks were laid out, and where certain files were, and what blocks were in what order, and how to list directories, but I never ended up doing that. So the pool disk only uses one block on the entire disk. The rest of it is blank. Disk 0 only has one block on it. Is that wasteful? Yeah, but oh well. The pool disk keeps track of how many disks are in the pool, where we can find free space to write data to, and a couple other niceties that, once again, are out of scope. After a nightmare of making block usage tracking work in the headers of disks, man, I'll tell you, I really don't like bitwise operations. And figuring out how to allocate multiple blocks across multiple disks in a clean way, it was finally time to store some data. After reading a little bit more Wikipedia, I realized that using inodes for storing my file system data centrally sounded like a pretty good idea. It's pretty much just a fancy pointer to a file or a folder. An inode keeps track of super basic things about files and folders, mainly where they are and when they were created, but the problem is, you need an inode for every file or folder that you want to point to, and you also have to store the inode somewhere. Thus, there's a dedicated block type for inodes, creatively named the inode block, which is our second block type after headers. Each inode block keeps track of how full it is, where it came from, and the rest of the space in the block is used to actually store the inode data. Only problem is, we have 501 bytes left over to actually store that data. I was pretty darn sure that I would need more than 501 bytes to store information about every file in Factorio, but I couldn't guarantee that all the inodes would end up in the same block, or even the same disk, or I didn't even know how many inodes I would need. Thus, inode blocks are linked together in a chain, starting at block 1 of disk 1. When you make a new pool, you make a pool disk, which is disk 0 that we already talked about, and a standard disk, although the standard in that name is kind of a misnomer since it's the only other disk type. Anyway, so disk 1, which is the second disk, gets a header as usual, which looks a little bit different, but you can ignore that. Then on block 1 of the second disk, we put the first inode block that starts our inode chain. So now if we're out of room for inodes for storing information about files, the final inode block in the chain will automatically expand itself another block by allocating one from the pool, which can create new disks, blah, blah, blah. It's complicated. Just know when we want a block, we'll get one. Or we'll explode. We make the new block, we point to the new block, and that becomes the new head of the chain. Then we put the new stuff into that. You got me? There's a gnat in my room. Where'd you come from? Did I get it? No, I didn't. Damn it. Where are you? A small mistake I made here was having the inode blocks only point forwards to the next block in the chain instead of also pointing backwards to the last block in the chain, but we don't usually traverse the inode list, so it ended up being fine. So now we can store inodes in a block and look them up later, right? Well, unfortunately, I wanted to be fancy with my inodes, and I thought I might as well try to save a little bit of extra space by dropping any irrelevant info. So my inodes are a variable size depending on the type of inode they are, which makes directly indexing into the inode blocks a living nightmare, which required a new type, and I also had to make that variably sized for some reason, man. It was a terrible idea. It overcomplicated things a lot. Anyways, inodes. We can point at a file or a folder using inodes, but we also have to store that information somewhere as well. Inodes don't directly point to the starts and ends of files or folders. They actually point at the beginning of directory blockchains and file extent blockchains. Let's look at how directories work. Overall, directories are pretty simple, but once again, big directories take more than 512 bytes to store, so yet again we have to use subsequent blocks and automatically expand and yada yada, just like inode blocks. And again, I didn't point backwards to the previous block, and I can't remember exactly why this was an issue, but I'm mad thinking about it, so it must have been really bad. That's the whole thing done. It's Purple Science's electric furnaces, productivity modules, and Rails. I have it all done. Anyways, the data that goes into those directory blocks are fittingly named directory items. Directory items are pretty simple, just a type that marks if the item is a file or another directory, a name for that file or directory, and where to find the inode that points to the block that the item starts at, whether that be another directory block or a file extent block, which we'll look at next. Fun fact, since Rust natively uses UTF-8 for all of its strings, you can name a file pretty much anything you want in Fluster, and it'll work just fine. Even this works. Storing files is a bit more complicated. Files start with a file extent block chain, which omically grows and shrinks just like directory blocks, but instead of storing a list of directory items, we store a list of file extents. Once again, only pointing to the next block, which made truncating files a pain, but we'll touch on that later. Each file extent block chain holds all of the information we need to reconstruct a single file and all of its data. Since files can be larger than a single floppy disk, or there might be holes in the block layout that we need to fill, and so on and so forth, files are broken up into runs of blocks called file extents. Each file extent is simply the start of an unbroken streak of blocks that make up the data of a file. Splitting them up into chunks like this lets us stick a chunk of a file literally anywhere we want. Overall, a simple concept, but once again I pre-optimized for size, resulting in variable sizes and such. It was a pain, but whatever. But that covers directories and files, which is really all we need, because nobody actually cares about symbolic links, hard links, sockets, all that crap, nobody cares. With the groundwork in place, it was finally time to start making files and folders using those blocks. But my plan was to make Fluster a fuse file system. File system in user space, or fuse, is a big ol' bundle of nerd crap that lets you run a file system on a Linux machine without making it a kernel module. Basically, Fuse is a simplified interface for writing file systems and gives us a list of functions that we need to implement. Only problem is, I use Windows, not Linux. There are some tools to let you use Fuse on Windows, but I could not for the life of me get the build chain of WinFSP or WinFuse working. So I had to switch to Linux. It is the year of the Linux desktop, after all. Well, not really. I wasn't about to migrate to Linux for just a couple floppy disks, so I ended up running Fluster and doing all of my development on it through Windows Subsystem for Linux, which had its own set of problems. I ended up needing to pass the entire USB device for the floppy drive directly into WSL after recompiling its kernel to work with floppy disks by using some networking jank called USP-IPD, which caused all sorts of weird issues, making the drive spin endlessly and sometimes not show up, but oh well. If it's almost broke, don't fix it. Why not a VM, I hear you cry? Well, Factorio in a VM ran on my machine at a buttery smooth 2 frames per second. So no. Now that I could finally build Fuse, I grabbed the Easy Fuser crate and got Fluster to mount for the first time. Yeah, it doesn't actually do anything yet, but it's a start. Since I wrote most of this months ago, the specifics are hard to go over, but I started filling in all the complicated logic for actually locating blocks on disks, automatically extending directories and such, and I wrote a lot of tests. I've never done test-driven development before, but man, it's totally worth it. By the way, Fluster is fully open source on my GitHub under the Creative Commons Attribution license, so feel free to use it in your file system design course as a case study on what not to do. I left a lot of comments to try to make my codebase more approachable as a learning utility and to document as much of my thought process as I could. So if you want detail on how this stuff works, go take a look. Anyways, after a bit more work, I could finally make folders. Then a few days later, I could make and edit files too. Around this time, I also started tracking how many disks were swapped in and out of the virtual floppy drive so I could optimize for it later. Disk swappage is really our #1 enemy here. Sure, the disks are slow, but nothing is slower than asking a sack of meat running on caffeine and autism to find disk 389 and swap it into the floppy drive.
But this just...
Early testing was a bit concerning. Writing 1,000 files with random small sizes to a folder took nearly 500,000 disk swaps, which... yeah, but with some caching and trying a lot, and I mean a lot of different cache strategies, I was able to upload the entirety of Factorio onto virtual disks in 12,000 swaps, then later I was able to get that down to 2,000, and finally just over 1,500. The final cache implementation is a 3-tiered cache with a customizable size. The specifics of caching and cache invalidation are complicated as usual, but basically the lowest tier on the cache copies for every read, and if we get a hit from that lowest tier of cache, it gets promoted to the next tier of cache, which uses a more complicated cache strategy that's based on access frequency. The cache supports reading and writing to blocks, and some other fancy nonsense such as flushing dirty reads directly to the disk right before we know we're going to swap. I think it was around this time that I had to switch to a more complicated Fuse library due to a bug with listing directories that was in the crate that I was using, and I couldn't avoid it. So I ripped out Easy Fuser and replaced it with the more complete but also more complicated FuseMT crate. Since the new crate was lower level, I needed to implement almost every single POSIX file system call myself. Some of these were pretty straightforward, but I wanted to be at least a little bit POSIX compliant. What did it cost? Well, fun fact. Did you know that the rename syscall doesn't just rename files in place, but can also move files to anywhere you want? This resulted in a 500-line monster of a function that does everything from checking the source and destination, checking if the source and destination are the same, checking if we're trying to move a file by changing it into a directory, checking for recursion, handling rollbacks of the file rename if it partially fails, etc., 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 all while having one of the most convoluted error schemes I have ever seen.
I was about to say, oh, I need to unlock filter inserters. Oh, I can't pre-do rocket fuel? Wait a minute, let's see magic trick. Bam.
Also, if you're nerdy enough, you might have noticed that we didn't leave any room in the inode data for file attributes, such as flags or permission bits. Luckily, we can just lie about most of it. Is having all of the permission bits set on everything and owning every file with root a good idea? No, it's not. Remember earlier when I mentioned that file extent blocks only pointed in a single direction? Well, there's another call that I needed to implement called truncate, which can shrink or grow files to an arbitrary size. Well, not pointing to the previous blocks in the chain was fine for when I needed to grow files, but it made shrinking files very complicated. Keeping track of all the extents and shuffling things around was a giant pain, resulting in yet another 500-line monstrosity of a function. Well, now that I'm POSIX compliant-ish, I could now read and write to files, delete files, rename files, move files, list directories, and pretty much everything you needed to do on a normal file system. And that's what this is. It's a, in quotes, normal file system. You really can do most things with this, but it is missing file locking, which does make a lot of software a little mad, but it works for most things. If you had hundreds of thousands of dollars, you could probably run Doom on this. Doom 2016, I mean. So with all of the theoretical work done, I ran a real-world test by saving and playing Bad Apple. First on virtual debug disks as a proof of concept, then on real floppy disks. That took many hours and uncovered a lot more bugs, but after fixing all of that, pretty soon I was successfully able to launch Factorio on virtual disks. Mostly. Then I made a functional terminal user interface, then ordered all the floppy disks. I knew from the get-go that I wanted to put custom label stickers on each of the disks, but product design, not really my forte, so it took quite a while to get something I liked. But eventually I got one, and then I ordered 2,000 stickers with that design on them. Except I accidentally ordered glossy stickers instead of matte stickers. Words cannot express how mad I was. Anyways, while waiting for the disks to come, I was able to trim down the install of Factorio quite a bit by removing things like translations and stripping the executable of all of its debug symbols, bringing down the total disk count to just over 1,000. I could have shrunk the game down a lot more by compressing all of the images, which account for more than 3/4 of the total size of the game, but I didn't want to compromise on the game's quality. Although, while doing the run, I did forget to turn on high-resolution sprites in the config file before launching the game, but yeah, I wasn't going to do that a second time, so oh well. After the laborious process of applying all the labels and wiping all the disks, it was finally time to actually put the game on them. Directly from the box, wiping the disks had around a 10% failure rate, so I'm glad I bought plenty extra. As for actually writing the game onto the disk, there was 2 approaches I could take. I could either load the entire game into memory, then save backups of all the disks and write them sequentially one by one, essentially making an image that I could flash onto each disk. Or I could mount the file system while it's completely empty and upload the files one at a time. I thought writing the game from backup was super lame, so I went with the latter, which was probably the biggest mistake I've made in the last 21 years of being alive. Well, maybe besides the goth girl at Denny's that asked for my number. I didn't give it to her, she was scary, and I regret that deeply. Bethany, if you're watching this, actually never mind, I'm still scared of you. The reason writing the game sequentially was such a bad idea was that the floppy drive was super unreliable through WSL USB pass-through, and I constantly needed to fiddle with it to make it work. And on top of that, I forgot to actually consider what would happen if a disk died while it was already in the pool. Guess who didn't write any handling for that? And guess who didn't make any backups? And had to start over? But instead of just flashing the game onto the disks using the boring way for my second attempt, I just added a backup and restore feature and added a troubleshooter for common issues. Then I failed to write the game again. 3 or 4 more times. One of the times I was literally 100 disks away from being done. Disk corruption. Eventually, I came to my senses and wrote the game for backups. Then once that was done, well, you saw me loading the game at the beginning of the video. We've come full circle. Bit all over the place, and if you don't understand how something works, well, chances are I've forgotten how it works too, but you can still ask me on Discord or email me. And with that, here's our rocket. I forgot to write in the script how long this took. I'll have to dub it in later. I'd like to take the usual moment to thank my supporters on Ko-fi. This video took way longer than I was expecting, and I got super busy with schoolwork on top of that, so that delayed it quite a bit. Sorry. While I was working on the video, a lot of people asked me,
why would you spend such a long time developing such a stupid idea that nobody will ever use?
It sounded fun, so why not? Just because ideas are stupid doesn't mean you won't learn from them while pursuing them. And learn I did, man. I wish I wrote down every time I had an aha moment. But trust me, I learn a lot. But that's all for today. My name's DocJade. Bye-bye.